Hello, my name is Matt Anderson. I'm a student at Georgia Tech, and this is a paper presentation for the paper When Your Fitness Tracker Betrays You, Quantifying the Predictability of Biometric Features Across Contexts. Before starting the paper presentation, I'd just like to take a moment to give a brief introduction. So I graduated from Brigham Young University in Provo, Utah with a BS in chemical engineering. Since graduating, I've worked at an oil refinery in Southern California as a process engineer. And so at the refinery, as can be imagined, there's industrial control systems and many PLCs, HMIs, RTUs, and obviously all the protocols are used as well. So this course has been really fun to learn about a little bit more about Modbus, and since taking this course, I've started to talk a lot more with the control systems engineers to learn a little bit more about the different systems in place. With that being said, let's start the paper presentation. The authors of the paper were Simon Eberz, Giulio Lovisotto, Andrea Patane, Marta, Kwiatkowska, Vincent and Ivan Martinovic. All were associated with the Department of Computer Science at the University of Oxford in the UK. In terms of an outline for this paper presentation, we'll start with an introduction discussing the common biometric approaches and really defining what is a biometric context. It's very important for this paper. We'll look at the threat model, followed by the experimental design, including the 5 different biometric approaches that the author selected, mapping methodology, which was definitely a lot of math, the results, and finally conclusion, what we can learn. Okay, to look at the introduction, biometric authentication can overcome shortcomings of passwords. The main password shortcoming that was brought up by the authors was remembering them. That can be difficult. The most common biometric approaches that we are familiar with are, many of us are familiar with, are fingerprints. One drawback is that these can be lifted from flat surfaces. An example would be coffee mugs. And the second common biometric approach would be facial recognition. Unfortunately, the drawback for this would be that 2D photos are readily available from social media. In terms of how the drawbacks, really how easy it would be for the attacker to obtain that information from a different source. Okay, so alternative biometric approaches to those two that were mentioned are behavior biometrics. Examples of behavior biometrics are keystroke dynamics, basically how you type, whether that be the force or the timing, mouse movements, touchscreen usage, swiping left, swiping right, how the speed at which you swipe, to what angles, what degree, and human gait, so basically how you walk or move. The gait is particularly interesting, mentioned by the authors, because gait data can be captured through cheap accelerometers, so cheap and plentiful, and any phone will have one. Most phones will have them. Okay, now for the biometric attack. So an attack on a biometric system or biometric authentication really has 2 steps. The first is the attacker obtains the victim's biometric data. The second being the attacker presents that biometric information to the authentication system. The focus of this paper is on the first step, obtaining the biometric data. So the presenting of the biometric information is beyond the scope of this paper. It's really focused on obtaining that biometric data. Okay, I mentioned I was talking about the outline about the definition of context and really what is a biometric context. Well, the biometric context refers to how and in what environment the biometric data is obtained. I think that an example may be the best way of explaining this concept. So the example that I chose to discuss was gait. So the context of gait biometric could be using a fitness tracker while jogging. The context of the device is a device used to obtain the data and the type of activity jogging while the data was obtained. So in this case, a different gait context could be while walking, or instead of a fitness tracker, a phone could be used. So when you think about gait, you need to think about the environment in which that information was obtained, as well as how that information was obtained. Another example would be with the ECG machine. They used 2 different ECG machines. One was a medical grade one, and the other one was a mobile ECG connected to a smartphone. So the context of the device used to measure the participant's ECG was different. Okay, and then the fundamental question that this paper looks at is really 3. And the first being, how can attackers obtain biometric information without compromising the template on the authentication device? The second being, are context-specific changes in features systematic and can they be predicted? And the third, how does this predictability impact the security of biometric authentication? And the approach the authors took was to derive a cross-context feature mapping based on population data. And I liked that statement because it really set it up for anyone reading to understand that this is an empirical approach as opposed to a theoretical or first principles approach. And that's important to kind of understand big picture what they're attempting to do. The authors, as opposed to trying to derive from theory how to transfer data between contexts or how to transfer biometric data across contexts, they look at the empirical data of actually two different population sets from context to context, and then attempt to create a function or find the mapping function that is able to transform data of one context to data to the different biometric context. Okay, and then for the paper contributions, really what this paper adds to the scientific community, the first being that it quantifies the predictability of 5 biometrics features and discusses the security implications. That's a key word too. It quantifies the predictability of these features. The first is ECG, second being eye movements, third mouse movements, fourth touchscreen dynamics, and fifth gait. Another significant contribution of the paper is a data set of 30 individuals for the 5 biometric approaches across several contexts is made public. So that required the paper authors to, round up 30 participants and collect data, and they made that database public as part of this research. Okay, now for the threat model. Basically, what a biometric attack would look like. What kind of attacker are we studying? So 2 definitions necessary for understanding the threat model are target and source. Target is the system and the context used by the system. Source is the context of the unsecure asset that contains biometric data from different contexts than target. Okay, once again, I think this will make more sense with an example. So as an example, if you're the attacker and the target is, let's say, a phone located in your pocket, in the victim's pocket, and this phone measures gait and keeps gait template for authentication purposes, the source could then be a fitness tracker, we'll say located on the victim's wrist that is unsecure but measures gait data. So once again, the attacker, he wants to authenticate or attack basically the target being the phone. However, he can't obtain the gait data directly from the phone, so he has to get it from a different source. Let's say the source be the fitness tracker. And really the key of this paper is to look at if it's possible, or how can you transform data, biometric data from one context, the source context, to the target context. Okay, so 5 assumptions were made in the threat model. First was obtaining victims' data usable in target context is hard because it is highly protected. It wouldn't be a very interesting paper, or well, I guess it would be a paper, but about a different topic if it was looking at how to break the security features of a phone to obtain that template of the victim's gait data, for example. This assumption is assuming that you cannot get at the data on the target device. Okay, 2. The victim uses another system that makes use of the same type of biometric data as a target. That's pretty self-explanatory. 3. The adversary can obtain biometric data from a population for source and target context. So both of those that we went over before. He obtains both source and target from a population, so from people other than the victim. 4. The adversary knows the biometric features used for recognition by the target system, but does not know any other detail used by the recognition algorithm. And finally, the adversary can reconstruct biometric signals from biometric templates and can inject forged biometric data into the target system. What this all sets up is that the attacker is able to obtain source biometric data. He needs to transform it to the target system. To do that, he's looking at trends across the population, source to target transformations. Now for the experimental design, what the paper authors actually had those 30 people do. So once again, 30 participants, and then biometric data for each of the 5 biometric modalities. Modality is just one of those approaches. So we discussed ECG, gait, touchscreen dynamics, across different contexts was collected from the participants. Okay, so for each of the 5, so for gait, really 5 different contexts, or 5 different fitness trackers were used. 3 smartphones, left arm, right front pocket, held in left hand, and then 2 fitness devices. And each participant took about a 700-meter run in the nearby park. I'm sure they look pretty funny with 3 different smartphones and 2 fitness devices. Okay, touchscreen dynamics was the second modality, and 3 different phones were used. high, mid, and low level phone. I put AKA expensive, mid-grade, and cheap. And they were basically measuring how the participants swiped, and they were looking at the different contexts there. For ECG, which is electrocardiography, I mentioned this before, but they used a medical ECG machine and a mobile ECG connected to a smartphone. For eye movements, the two contexts were calibrated versus uncalibrated eye tracker used to obtain the data. And then for mouse movements, they used a mouse versus a trackpad as the two different contexts. So mapping methodology. I mentioned previously that that word quantify was important because they were going to, instead of qualitatively looking at which one was better, they were going to put some numbers behind the different biometric modalities, really which one is most resilient to cross-context attacks. So to summarize all the math that was presented by the paper, I would say that it comes down to an optimization problem that was to minimize the error of mapping functions for each of the 5 biometric modalities. It basically looked at the two populations from the different contexts, and then it attempted to have a function that would transform biometric data from the source context to the target context, and it's going to minimize the error amongst the entire population. So the authors decided to focus on linear functions due to the potential of a large population sizes, which is fine, but they did also perform optimization of polynomials at different degrees, degree 2, 3, and 4, but none of these nonlinear functions provided results that were statistically significant, that were different by a statistically significant amount than the linear functions. Okay, I put this here just to, really if you were to fast forward my video until this point, this is the most probably important concept, is that their linear cross-context mapping function, which they made, takes source biometric data and transforms it into target biometric data in an attempt to then break into or authenticate the target device. So the first metric that they came up with to look at the different modalities was an unpredictability score. So they called this U, and it can be range from 0 to 1. If you're U, your unpredictability score is 0. What that really is saying is that the differences are systematic. That this cross-context mapping approach is able to accurately map observations from the source context to samples from the target context. So from a security standpoint, that's probably that is not great. And if your unpredictability score equals 1, that means that the differences between the jth feature values in the source and the target context cannot be systematically predicted in this way. Very unpredictable. So that jth feature, really that word feature, the unpredictability score is not for an entire modality. So for example, it's not for gait in general. It's for specific features within gait. A feature of gait or how someone walks, for example, could be the rate of your steps, kind of the time between steps. It could also be the height to which you raise your thigh was a different feature. So each feature of each modality receives a different unpredictability score. And for that reason, the authors created a weighted score. So I guess I got ahead of myself, but the unpredictability score U is obtained for each feature of each biometric modality. And the desire of the authors was to aggregate across the whole biometric modality, so all the different features, really as opposed to each feature. They wanted one number that could compare the total kind of weighted unpredictability. So the weighted unpredictability score, which they referred to as WV of a biometric modality, depends on the scores of the individual features. And distinctive features contribute more to unpredictability score. The authors state that the absolute value is not very useful of this weighted score, but the benefit is that you're able to compare the 5 different modalities and really see which ones are most resilient to cross-context attacks. The results, I know that you by now are on the edge of your seat. Okay, so this was how the authors presented the results, and I just wanted to focus in on the bolded section, which is really the average of each of the 5 dynamics, so ECG, eye movements, mouse movements, touch dynamics, and gait. And I wanted to highlight gait. The higher unpredictability score, weighted unpredictability score, signifies that gait among the 5 could be considered the most resilient to cross-context attacks. Another way of saying that is that gait was the most difficult to transform source data to target biometric data. And if you go to the other end, mouse movements, eye movements, and touch dynamics, all three were much easier to predict the target data, really transform the source data to the target data. Just a brief statement on each of the five. So for gait, the authors noted it was particularly resilient to cross-context attacks. For ECG, the type of sensor has a significant impact on the weighted unpredictability. That's what the authors observed. And then for eye movements, they were highly predictable. For touch dynamics, the high-quality sensors can improve security of authentication devices. So more expensive, not necessarily more expensive, but higher quality sensors, which are normally correlated to more expensive phones, can help in that situation. And then for mouse movements, they noted were easily predicted across contexts. One other interesting observation they had, and on the x-axis of these plots is the mapping population size. So as you increase your population size, the unpredictability score decreased, but up to a point. There was a diminishing return above a population size of about 10. So beyond 10, they didn't find much improvement in the unpredictability scores. Okay, and now for the conclusion, really what we can learn from this paper. So one of the main contributions is the construction, the biometric threat model is assisted by this work. This is certainly something that I hadn't considered before, a cross-context attack on biometric authentication. Different contexts can be more useful than others for cross-context biometric attacks. This is also something I hadn't considered. The authors note that ECG and gait are up to twice as unpredictable across contexts compared to touch dynamics, mouse movements, and eye movements. And who can learn from this really are engineers and those responsible for security, and they need to be aware of what information could be available to the attacker. Knowing that certain biometric modalities are more susceptible to cross-context attacks, and knowing what information is available to the attacker should be a consideration when developing biometric security systems. And really just that last statement is that consideration should be given to avoid certain features that are shown to lack resilience against cross-context attacks, and maybe it would be best not to use those features that really don't have that required resilience. If you'd like to learn more, I encourage you to read the entire paper. There's a lot of good information, and thank you for watching.